1040, moving stones until consecutive. 2. On an infinity, let's be talking about infinity. On an infinity number line, the position of I stone is given by stone sub I equals stone and end stone. Endpoint stone that has the smallest or largest position. Each turn, you pick up an endpoint stone and move it to an unoccupied so that it's no longer an endpoint stone. In particular, if a stone is at on turn 5, you can now move the endpoints at position 5, since moving it to any position will keep that stone as an endpoint stone. The game ends when you cannot make any moves, i.e. the stones are in consecutive position. When the game ends, what is the minimum and maximum of moves you could have made? The answer is in a way, just return the answer in some way. Okay. Do we have to sort this? Oh no, the Ive stone. Okay. Does that really matter? Has the smallest or largest position. So isn't the 4 endpoint stone? You cannot move that stone at position 5. Oh, okay. Maybe. It is a little bit. Sorry, I'm still understanding the problem with this one in general. Okay, well, 1, 2, and 5, you cannot move 5 because it doesn't change it. An unoccupied position? Wait, why can't you move the 5 to 0 or something like that? Oh, well, actually it tells you. Okay. So the 1 and 2 are done. Okay. Does this matter that the inputs are in a weird way? Still trying to figure that out. Like, why would you just not sort it? I think we just sorted, right? Okay. Well, yeah, speaking about giving structure to a problem. Yeah, okay. Wow. Yeah, I think first of all, I think I would just sort the input. It's usually cheap, so like now you can think of things without kind of worrying about, I don't know, weird edge cases in general. And n is 10 to the 4th, which is 10,000, I suppose. Excuse me. Or 100,000? No, it's 10,000, right? Pretty bad at that. Um, well, max move is 3, 4, 6, 10. That is a weird one. These endpoint. Okay. I think right now my head is just thinking: is there a pattern that I can kind of abuse? I mean, clearly the answer is, if all the answers are, or if everything is already good, then it's 0. But so 3 to 7, 4 to 8. Okay, 5 to 9. Basically, you always want the result to be all consecutive. That's when the game ends. Oh, well, I guess it tells you that. So points for me for reading. But so what is the minimal move? I guess this has two problems. The first one is the minimal. I feel like minimal is a little easier. It's let's see if I move my pencil out so I could kind of just visualize this a little bit. Okay. I could just draw here more ASCII art. So 3, 4, 5, 6, 10. The shortest will be so there's 10 to the 4th element, so that's too much to do anything even n square. So, and this is a little bit of a meta kind of thing, but well, and n log n will probably be okay. I mean, n log n is definitely gonna be okay. It's just I don't know how many albums are there will be requiring n log n, that sort of thing. So it's probably gonna be something linear-ish after the n log n. So it's probably some sort of greedy-ish. It's a tricky case to get the minimum even, because you normally you would just like move the 10 to the 7 and be like, oh, that's fun. But in this case, you actually cannot move the end stone, so it's to the middle. What happens? You have two sets of essentially like islands, right? Well, so 3 to the 7. This is also probably like they give you like a way that makes sense, but it might not be the way that you need to construct. I think so. Given these, I think the way that I would actually move it minimally is actually move to 6 to accommodate the numbers that are needed. So in this case, you only need a 10, so you create one space, move to 6. It's not a 6 anymore, but it's 6 there, and then you put 10 in the old 6. So this is 10. And then this is now sorted, kind of. Or these are now consecutive, right? And you could, and my conjecture is that if you have the longest island of consecutive stones, so let's say you have essentially this, but let's just say 15, 16, 17, you still, well, in this case, maybe that, so you would move 6 and then create 3 spots, say, and then just move 15, 16, 17, and obviously if you have more numbers, then you just do that, right? Like create more space. So then it's always going to be essentially your minimal move may just be a function of your longest consecutive thing. That's my guess for the greedy minimal. Yeah, there may be a weird edge case that may be the same, where like I don't know, like 8, 9, 10, because then in this case you want to make space for 3 things, but 6, 7, 8, 9. So you move your 6 here, but it's technically on the 9th position, so you can't. What would you do then? For the minimal. Well, I guess in that case, if the 9 already exists, then we don't even have to move that for the minimal, because then if the 9 already exists, then we already will use the 9 as the endpoint. And then now we don't have 6, and then 8 is taken, and then 10 is here. So actually I just end up being 1 move. So okay. So I think for minimal, you would create that number of space and then the number of movements will just be the stuff that's after that, and then move it into that slot, I would say. And then now, and we have to also consider the case of, I guess it could be negative technically, but it doesn't really matter. And then you have to consider a case where there's numbers on both sides. Now you have 3, 5, 6, say 8, 9, 10. There's a lot of things to consider. I think actually though, what ends up happening is there's some kind of rolling window characteristic. Maybe. So let's say you want to keep the core together, but so maybe that's not sufficient. But oh, actually that makes sense. Now that I think about it. Okay. I think I have a better formulation of what I want to do now that I'm kind of analyzing this problem way too much. Basically you have, what is it? 10 numbers? No, that's 9 numbers. 9 numbers. So you just do a rolling window starting and then just count. And then it's usually math to do the rolling window on those numbers to calculate how many things are already in place, and then you move out of it for them, something like that, and then just do the math maybe, something like that. I'm a little really hand wavy to be honest, because I don't know. But basically, like for example, this has 7, so you know that, let's say your initial thing though, so we have to be really smart on this rolling window, so you can't just like do it that naively. Or like you can't just have like a Boolean array value type thing. It's tricky for a medium. Maybe I should have done moving stones until consecutive 1 first, but and I didn't even do the maximal move yet. But for example, in this case, we know that we want three numbers to consecutive. So then first we check 5, 6, 7. We know that within the set there's 1 number. So that means we have to move 2. And in this case, can it even be done? Let's say this is our current window. Oh, actually, this is sorted, so actually, I don't know why we represent it that way. Okay, let's start with the first window then. So then now we have 2, 3, 4. We tried that on the current window. Can this even be done? Because you would have to move to 7 to endpoint stone. Oh no, whoops, we can only move an endpoint stone. So actually, maybe that probably makes the problem a lot easier, and I'm just terrible at reading, because then, yeah, okay, well, let me rethink this for a second. I think I just tried to solve a different problem. For some reason, I thought you could move any stone, but I just noticed that you could only pick up an endpoint stone. That probably changes things easier, but okay. Because then now, okay, let's start over. Let's say you have 4, 7, 9. Okay, so now you can only move to 4 to 9. So if you move to 4, the only place you can move to is to 8. I guess that finishes the game. And if you move to 9, you could do it to 6 or 7. I guess it doesn't really matter, does it? Because if you move it to even 6, then like you keep on like frogging. So I think okay, maybe I mean it's still greedy, so that part of the analysis is probably gonna be right. But since we can only move to end stone, man, I misread that. Okay, because then I could move to 3 to the 7 as the first biggest number that's not on the thing, and then 4 also, and then so the smallest number move is just what is the smallest number or minimal moves? Because you can't move to, in this case, you can't move, you have the 3 and the thing, so you could only move to 3. I mean, and you could still do that thing where you create space like I was saying, but it'll take 2 moves. But that seems like they'll have so many edge cases that I'm kind of scared. I think the consecutive piece is probably the rare one. I feel like the maximal one, now it makes sense. But you just keep on marching things down. You look at the next number and then you just well, can I define this? If it's greedy, what is the, maybe I could think about it in terms of the subproblems type thing instead of just strategy and improving it greedy. But and we have at least 3 stones. I wonder if this is also like a special unique case where you're making space. But can I still use the rolling window concept? Because like, let's say you have 3 to 7. Well, this is not possible to get to from 3 to 10. But now when we try this as your window, well, then now you'd see that we can move the 3 to the 8 and then 10 to the 7. Is that even reasonable? And that's just 2 moves. Then move out 5 to 9. And now you move the 3 to the 9 and then 4 to the 8 and then 10 to the 7. Yes, that's a possible thing. Oops. Now our window is 10. Well, then it's not possible, but right? Because you have to move to 3 to, I guess it's possible. You just move to 3 to the 14 and then fill it in. But that is so weird. Is it weird? Here you move to 3 to the 13. You move to 6 to the 9, and then can you always, I guess my question is, can you always do this in a, is it always just a diff? Like, I think that's the thing, like, given this, yeah, clearly, the answer will be 2 is the diff, but then like here, obviously the diff is actually impossible because the diff is 1. What about that's also impossible. So maybe one move will never be, because you can. This is the case where one move is good, right? So you have 4, 7, 9. I guess 7, 8, 9. So the difference is 1, and you just kind of move things in. Wow, I think I'm a little bit lost on this one. All right, let me just use a hint then, real quick. Cows? I didn't even know they're cows. Is this might not even be the right hint. Do they mean stones? Anyway. Man, this hint is very hard to read. Did they copy this off like Yusako or something, where they always use cows as a thing? Yeah, huh. How do I choose? Man, I'm getting stumped by a medium. Luckily, that didn't happen during the contest, but okay. I mean, 2 numbers are already in place, and you can move one of them from the outside. So, I mean, obviously this is 1, but I'm trying to figure out how to do the 2 thing too. Well, 2 is, you do 4, 5, 6, I guess, but okay. I think maybe this is the only edge case. I think that's the where you have to do the math on yeah, you have to do the math on whatchamacallit. You have to do the math on just moving 1 and then double checking the endpoints. Because the 10 will not go to 2, right? You have to move. You have to check that the point you're moving is not on it. Okay. Yes, that's for the lower bound. Maybe I should. I mean, maybe that hint was essentially it, but okay, let's do minimal first. What's it called? Okay. What is my window at? Okay. Oh, I guess I should count. So, number of stones, and it's equal to is it 10 to the 4th? So you really cannot do some n square thing, right? That's like 10 to the 8th. That's bad news. Okay. Basically, we just have to keep track. Yeah, I guess actually I'm wrong when there should be symbol. Just keep track of number of things that are in it. Okay, let's just try to just do the math. So then there should be, so at 4 we want to check what do we, it's coming. Do we need to check all the numbers around it? Because then I could get to n square. I guess all the numbers that are around it will always only have one number. Okay, so if we do it that way, then let's keep track of the rolling window. That one doing it in a way, or if I could do it in an implicit way. Yeah, okay, this does not make sense. So let's say that this is the head of the thing. Oops. While head is less than index and stones of head minus stone. So the difference is bigger than n. Okay. So the cost now is minimal is equal to the number of things that are not in. So the number of things that are in is stone minus head. Oops, index. And then n minus this, maybe minus 1 as well, but so they equal then, okay. Okay, I mean, I didn't handle the edge case, but maybe that'll give me something to play around with. Hmm. No, I mean, I knew this is not right because I don't return half the answer. Okay, so it's one for the sec. Oh yeah, because we did not handle that, which we know. But at least the maximum matching part should be right, I think. Okay, so score is equal to this thing. So how do you define the case where this is not a routed move? Or that it takes two, rather. Because here you could actually move. I guess it's just one or the other. And it doesn't really matter which way it is. But here, then clearly you move to 3, and so then you move 2. So if the is it just like literally if score is equal to 1 and how do you define this corner case? Like this literally. Oops, not this one, but this literally. Oh, thanks for the follow, Goldilocks. Hopefully I find the just right response for this problem. But okay, so score is equal to 1. I guess this only happens when score is 1, which means there's only one thing to move, right? Because even if there are more numbers, like I say this, oops, let's say we add 1 to it, even though we do something like this, well, then there'll always be 2 anyway. Is there a way to get this to 1? So this only happens if stones up. So if this is equal to what does this equal to? Okay, let's just print it out. Oh, actually, I don't know why you would print out that part, but what is the state of the world? Okay, so stone sub head is 7. How does that make sense? That's not, is that the right form? Oh, that's not the right form. Oops. Okay. So at 3, which makes sense, and the stone we are doing is 6. Okay. Oh, okay. So that means everything else is consecutive. So is equal to n minus 1, 3, n plus 1. Then score is equal to 2 because you have to do this thing. Okay, that was 6 minus 3 is 3. We want for 4, which okay, n minus 2, fine. Okay, I mean, so I think that's, oh man, that's just very tricky, but okay. Now I have to figure out how to do the max, which I think is a, yeah, we use the hand so much, but for the max we have to lose either the gap 8 minus. So basically either the last 2 elements or the first 2 elements. But okay. I mean, that's a hint, but I have to figure out why that is the case. So maximal is okay. Well, let's think about it. First 2 gaps, so 10 and the 6, right? That's the biggest gap. And then we have 3 moves because people could just move the 3 into the gap in between, so that because every other so the I guess the greediest move is to or the maximal move is to move the stone to one of the endpoints into one of the into that gap, I suppose, in between the first 2 numbers or so, or the other way around, and then kind of keep doing it, because otherwise, because if you don't do anything in that gap, is that always true? Yeah, because then you otherwise you peel off other stuff, and then you still need to fill it. But what if you have like someone like 1, 3, 5, 7, 9? Then when you just do the 9 to the 6, and then 1 to the, well, this is maybe a bad example, but still, do 2. Maybe that's not right. Is it just like the number of gaps? Because, so basically what you would want to do, I imagine, is just actually to move a stone, you either put it in one of the 2 places, which is an endpoint, and then move it to the place immediately to the right of the left, or the other way, which is to put it and just keep on filling it up. Is that really the slowest? Yeah, this problem is so annoying, I think. Well, I think the invariant, what is the invariant? The invariant is that given I guess we start with x. The invariant is that for the maximal move, well, we just fill up, in this case, is it just the number of spaces? Because in this case, we'll just do one, we'll keep on moving and then we move the spaces, and then it will take one move to remove a space, except in that case where if it's like this, then you would have to move one of them first to the other side, in this case, yeah, to here, and then get rid of this edge, right? Maybe that's what they say about a gap. And then now you move things one by one to fill up all the gaps. So, okay. And the number of gaps is just n, well, not n, but the smallest number minus the biggest number minus the n, and then you subtract from that the smaller of the gaps between the left endpoint and the right endpoint. That probably makes sense. Okay. What a crap problem. Okay, let's say maximal starts with, what were we saying? So storm is the last one minus storm sub 0. So that's the number of space minus n, number of gaps, and then minus 2 or something like that. And then now that's the number of gaps, and then we subtract from the number of usable gap the minimal of storm. It's always 3, right? Okay. Minus 2 or storms of 1 minus, that's right ish. So I'm a little bit of a low. Well, let's see. I don't know. I'm just a little tired. Usually I would maybe actually question it and test it more, but let's just get a test case. Okay. Never had an issue here. Wasn't this one of the examples? Nope. Why did I get 0 for that one? Probably deserve this error. Well, clearly it should not be 0. Let's move the 5 to the 9. Oh, my rolling window may be wrong. No, but still should not put 0. Why is it 0? Maybe there's an off by 1. It's probably not 5-1 to be honest. Like with this maybe. We want this to be want this to be maybe this just because of an off by one. If it's inclusive, yeah, okay, fine, maybe. Let's try again. Sorry, friends, if I seem a little low energy. This problem was just a lot of thinking. I mean, the coding is very straightforward. I think some of that is just like you have to prove to yourself so much because once again, a lot of this is like greedy-ish, and greedy for me is always a little tricky to understand. With greedy with like that one case of well, this case took me a long time to um, con- convince that this is the only edge case. Like I drew it all out to kind of figure it out. Um, but yeah, let me go over this problem a little bit and I think basically just in a meta sense, and sometimes you cannot use that in an interview because you can't tell them like what size you're trying to fix. But then you could talk about your thought process through it. I think for me, saying that n is 10,000 means well n square albums out of the way, so you could only do n log n or something like that. And sorting is n log n, but even after that, you want to keep your constants low. And this doesn't feel like a divide and conquer type equation problem for me. So that in the sense that like yeah, I don't know. For me, it's just a little bit of intuition, but it didn't seem like a divide and conquer because there's no easy way to like divide the problem into sub problems that you can merge later, right? So that's the way you would think about it, and that would be an n log n algorithm. So that means it must be of n, which means that it's some sort of greedy and maybe even rolling window, which was what I was even got in a little bit early, but yeah, just saying rolling window doesn't mean you know how to salvage using rolling window, and that took me a long time to convince myself that this is the only, or not, well, this is the only edge case where it's one, and they show you in the examples, uh, and yeah, and it's basically a version of working backwards of you can only pick up an endpoint stone. So that was an issue that I was facing. And then after that, the minimal was easy, minus a off by one. I should double check that, but I was just a little tired near the end. But yeah, and I also like that the hint still refers to cows, so I could almost willing to bet that this is a user code problem, which is what sadly high school students used to practice, and I'm struggling with it, of course. But yeah, and then Maximal, I think it's much easier. I just didn't think about it until like near the end because I was worried about the other half. And yeah, and basically just a simple math of like, okay, here's all the gap. It doesn't matter how you. And I think I focused a little bit on this case a little bit too much. I think the more kind of typical case is something like this, where, well, how many, what's the maximal moves of something like this, and having this visualization helped me a little bit. So I was just focusing on the numbers and kind of, I don't know, like one layer is removed a little bit too much probably, but this allows you to be like, okay, and I kind of drew this a little bit where you move these things one by one from the endpoint, and it doesn't really matter which way you go after this, right? Because you know, because you can easily move this to whatever, and if you count that way, then the answer is obvious that um, the number of gaps is your maximal moves because you can always make a justification for that, and then the only edge case as well, because you have two, then you could like do that stagger thing, like they'll move to get through life together as if a pointer or whatever, and then just keep going, right? But if you have one, then as I was mentioning, then well, you lose the first gap before you close this gap, and then move one by one and to fill in the remaining gaps, right? So that's kind of and then you, because of that, of greedy-ish, you always want to, or you only have one decision, which is to choose the shorter one, and then everything else follows anyway. So yeah, so that's kind of the problem. I don't know. This is way brain teaser-y, maybe a little bit. There's a lot of just like really understand what it means to kind of follow the problem, which makes it a fun problem to solve as a brain teaser-y thing. But and this is probably a problem that's way typical of like I was saying, years ago, and other competitive programming things. So definitely something that I enjoy practicing, and also a little fun in retrospect. But when an interview is always going to be a little iffy and always a little bit tricky, and you're always not going to feel great because you feel like there are a million questions, and you got one that requires like this level of mental dexterity, which maybe is fine if you're, especially if you're doing well. But I always have a thing against greedy algorithms in general. It's just my personal nemesis. That's all. So yeah, but yeah, I don't know how much you can learn from this problem in the sense of something that you can extend to your further learning. So I would definitely recommend learning or like practicing other problems before working on this one. Uh, in terms of coding complexity, I mean, this is n log n plus O of n. So n log n algorithm. I don't use any extra space other than O of 1 to hold variables. So yeah, but of course sorting is in place, so you can make some argument there. But yeah, that's all I have for this problem, I think. So yeah, I hope either you really understand this problem or you don't get this on your interview if you have an interview.